Hi, this is Michael Levin and analysis of World Finals 2016 problem M. This is one of the problems considered not very hard, but the trickiest part is to really understand the problem statement. And then, if you write any reasonable solution when you understand the problem statement, it probably will pass. So let's start digging into this problem statement. This is a problem about tasks and instructions and resources and a protocol called priority ceiling, which basically guarantees that if you execute the tasks which can lock resources and block each other because of that, the programs will still go through, all the tasks will be executed, and you need to determine when exactly each task will finish its processing. So each task T has a start time S of T. It has a base priority BP of T, which is used in the protocol to make sure all the tasks will be finished at some point, and a list of instructions. Each instruction I is either a simple instruction to compute something for 1 microsecond, or an instruction to lock some resource K, which takes no time, which is immediate, or release resource K. And it is guaranteed that all the resources locked by instruction I locked and released in some reasonable order, so that you always release the resource you locked last, and so you don't get any task blocking itself and strange cycles because of strange locking and releasing order. So there are a number of resources, and for each resource we can define a set of tasks which try to lock it in the list of instructions. And then you define priority ceiling for that resource as the maximum base priority of all tasks that try to lock it during the execution. And this is the main value we use to make sure that everything will work and all the tasks will finish. So now what the processor does, we have only one processor on our machine. It starts with setting the current time to 0, and then it runs an infinite loop with the following 3 steps. First, it tries to identify all the running tasks, and the task is considered to be running if the current time is greater or equal than the starting time for the task, and not all the instructions of the tasks are already done, basically, so it's not finished. If there are any running tasks, then we need to determine which tasks are blocking each other and what are their current priorities. Their current priorities can be different from their base priorities. So, a task T1 blocks a task T2 if one of the following holds. First is easy. If T1 owns resource K, that is, it locked resource K and didn't release it, and next instruction in the task T2 in the list of instructions is to lock resource K. So T2 cannot do that, that's why T1 blocks T2 from execution. And second condition is a complicated one. If T1 owns some resource L and the priority ceiling of that resource L is greater than or equal to the current priority of task T2, which we don't know yet what it is. However, the definition of current priority is maximum of the base priority of this task and maximum of all the current priorities of the tasks that it blocks. So it is a kind of a circular definition, but the problem statement ensures us that we can resolve all the cycles in this definition, and there is a unique set of current priorities that satisfy these conditions. So we can uniquely define which tasks are blocking each other and what are their current priorities. So after we determine that, if we have at least some task that is running, we run the highest priority task, the next instruction from it, or if there are no tasks that are running, we just increment current time. So this is what we basically need to simulate in our program. And the only problem here is to determine the current priorities and who blocks whom. And the part when some task owns some resource is easy. We just have a graph of tasks and some of them own some resources and block others because of that. And the second part is tricky with cycles, but the key insight here is that if we have point B when T1 owns L and blocks T2 because of that, then it means that the priority ceiling of resource L is greater than or equal to current priority of task T2. But we also know that current priority of task T2 is always at least the same or greater than its base priority. And from the other hand, priority ceiling of resource L is less than or equal to base priority of task T1 because of the definition of priority ceiling. And so it follows that if task T1 blocks task T2 because of point B, then base priority of task 1 is at least base priority of task 2. So we can basically resolve blocking via sorting by base priority. And we can always determine one by one which task is blocked and which task is blocking. And then when we found the task that is the lowest in the hierarchy, which is blocked but doesn't block anything, we can determine its current priority based on the definition and then proceed to the next task and so on. So this solution will do this on each iteration, basically simulate what processor does, and the hardest part is to find the blocking and the current priorities. So how long will it work? Well, we know that at most 10,000 seconds will go before all the tasks will be running, and this is denoted by max S, max start time. And then after that, we will need to implement at most number of tasks multiplied by maximum number of instructions in the list for task instructions, which will take the corresponding number of microseconds. And for each such iteration, we will use at most number of tasks multiplied by number of resources time to resolve the blocking and the current priorities. And this is all good enough because we have at most 20 tasks, at most 20 resources. Starting times are at most 10,000. And the total number of instructions in each list is at most 10,000 because we get at most 100 lines in the description of each task, and each line can be either lock resource, release resource, or compute for at most 100 times. So that gives us 10,000. Basically, that's all.